here for the introduction. Hello, everyone. I'm Nitish. I'm a researcher at VITO. I'm part of the team Energy Systems and Conference Optimization, also known as ESCO. This research is part of a Horizon Europe project, which is called as Hook Loop. And in this presentation, I'm going to show you some part of that research. So, which is about the thermo-hydraulic analysis of concentric pipes, which take part in certain kind of geothermal power plants. Let's understand why do we need like concentric pipes in a geothermal application. Like a conventional geothermal power plant would have two kind of drills. One will be a producer, other one will be an injector, and you will have transfer of heat through this geothermal reservoir. And because of this geothermal reservoir, which is open, you have a lot of leakages into the environment, and you can have a lot of cyclic effects or contamination of drinking water. And that's why you will realize why geothermal power plant has not really picked up so much in the, let's say, in this strive towards the sustainable energy. Now, to fix that, there is an alternative in which what if we make the system completely closed, in which we have polar fluid going from the surface to the crust or this geothermal reservoir, and then we have a return pipe which is right embedded inside this drilling, which is very interesting, but there are a lot of mechanical or let's say design challenges. There are a lot of them, but I will restrict to the one that is most interesting to me, which is if you look at the flow physics close to that area towards the end. Now there you have different sections. So you have the hot fluid, which is kind of coming back. You have insulation layer, and then you have the layer of cold fluid, which is kind of coming into the reservoir area. And this one is nothing but the area where the flow turns and then returns to the earth. On the sides, you have the ground, so from where the heat transfer takes place and the cold fluid gets heated up. Now, as you can imagine, on an ideal world, this sounds very beautiful, looks amazing, should work. But obviously, if you think of it, the central pipe is very difficult to keep centered all the time. If you want to do that, you need to apply some kind of centering devices in your drill so that everything is centered, but that's never the case. So there's always certain kind of lag, like it kind of is a bit off-centered, and the worst case is touching the bottom of the cold pipe. So the question is, we do not know how much is the loss in terms of heat transfer or let's say in terms of pressure drop in these kind of systems. And this is what is the objective to understand for us. So that's why we study the effect of eccentricity, which is nothing but how much does the inner pipe offset from the outer pipe. And then we also investigate if there are alternative ways with which we can increase the heat transfer in such a system. So I will represent eccentricity as C. So where C equals to 0 means both the pipes are centered, and C equals to 100% means that the inner pipe is sitting at the bottom of the pipe. Now, if you look at the methodology, if I go back to the same image, and if you look at a smaller section in this horizontal section of the geothermal power plant, you will realize something which is very common, or that we have a functionality in SU2, which is seamless periodicity. Now, also we try to choose an area which is over here, because this is a horizontal section which is approximately 2 to 2.5 kilometers long, and that at the center the properties are more or less steady state, and everything is they do not change as much as compared to if you go to one of the areas on the other side. So what is streamwise periodicity? Just to give you a brief overview. So if we have a flow field or any kind of channel in which we have areas which are changing in a more periodic manner, instead of simulating the entire periodic domain or the entire repeating structures, we can just simulate one part of this structure, and based on this, let's say this assumption of streamwise periodicity, we get additional source terms which take part in your momentum and your energy equation. Based on that, just by simulating this one single domain, you can predict the performance of your entire channel. So we use the same solver in this case, and we try to kind of model this part of the tube. However, in the current study, we only limit ourselves to the cold fluid only, and we will come to the reasons why later on. And I use the version 8 of SU2, which has the implementations of Tobias. This is my combinator setup. So I use the incompressible Navisto RAM solver with seamless periodicity and with turbulence. And if you look at the boundary conditions, I have at the inlet and the outlet the seamless periodic boundaries and the inlet diameter. So in this case, the inner part has insulated wall, whereas the outer side we have a heat flux that has been specified on the wall. This is just an example mesh, and these are some of the values. So more important is the heat flux and the temperature quantities. So as you can imagine that the properties in this such kind of power plant can really vary a lot with time. So we take the heat flux and temperature quantities from a system level simulation at year 10. And it is kind of assumed that after year 10, the properties are more or less constant. They do not change that much in the rock. So that's why we take those kind of properties. And also, since we are doing streamless periodicity, we are simulating a very small part of the pipe. So if you pour this in a reflux, the temperature increase is like minimal. So in order to make sure that our solver doesn't really like suffer from getting some delta T's, which are very, very small, which can also lead to sometimes catastrophic cancellation in SE2, we increase the heat flux value by a factor of 1,000.
Nitish, the temperature is 577 Celsius. No. 57, sorry. 57?
But the fluid, yes, I think. Yeah, 57.
Not a lot.
But for the cold side,
Okay.
it's for the cold side. So before going into, let's say, studying the full eccentricity, we did the simulation with eccentricity of 0, and we compared the friction factor and Nusselt number with the parameters that we can find in open literature. So in this case, you can see the friction factor was compared with the literature from Dixon and a reference article that is used in the part of this in your project, and same for Nusselt number, in which we compare with VDI and in the reference. And you can see the values are pretty much in the same ballpark. So we can say that the CFD is able to predict the performance as per the reference article. Now let's look at what happened with the study of eccentricity. So on the top left, we have the heat transfer coefficient. Okay, I top left. Yeah, okay. Top left. On the right, we have the area distribution, and the bottom we have logarithmic temperature difference, and on the right we have the velocity magnitude. Now, what you can see that there is a black and there's also a gray line. Gray line is for eccentricity 0, and black will correspond with the eccentricity of the slide, the number that is mentioned on the slide. And as I move down, you can see so what is interesting to note here, or the most important takeaway here, is that your logarithmic temperature, it increases dramatically at the bottom section of the pipe, where your inner pipe is almost touching the outer pipe. And majorly because of this reason, you can see that the local heat transfer coefficient also reduces dramatically. These are some contours, nothing very fancy, very simple. These are the temperature, and you can see over here you get a very high increase in the temperature. If I look at the variation of the properties with eccentricity in terms of friction factor, you can see that the friction factor reduces as much as 25% in this case. And if you look at the Nusselt number, we get almost 70% decrease in our Nusselt number. And if you look at the real reason why this is happening, it is primarily because the lines over here in the bottom, they correspond to the inlet and the outlet temperature of the fluid. And you see, as we change the eccentricity, these values do not change dramatically. However, what changes dramatically is your water temperature, which leads to your change in your logarithmic temperature difference. Now, a big, let's say, asterisk here is that this is perhaps because we are using a heat flux wall. And this is kind of limiting the heat transfer from that area. And that is not 100% true, because in a realistic case, we have a casing, a pipe, which can allow for this heat to move around the fluid and can reduce and can improve the overall heat transfer performance. So it doesn't take into account the conduction part that can happen along the pipe, which is a bit of a drawback in this particular simulation. Now, in order to increase further the heat transfer, another part we wanted to study is what happens if we can generate certain kind of fins on the outer geometry of the pipe and see if we can increase certain kind of heat transfer. Now, we tried a lot of fancy fin generations, and it was very difficult to simulate or to get them converged. But these are some of that we managed. And obviously, at the first hand, we had like, okay, maybe we can get some fancy fins or something, but it is very difficult. So in the end, what we managed to create these kind of ribs around the outer pipe, and these were like kind of generated using FFD box. So we made a radial FFD box and deformed everything towards the outside or the inside. And based on that, we were able to get six different configurations. So although we wanted to improve the heat transfer rate, we were not able to constrain it. So instead, we tried to improve the pressure drop. And what we see that for the section with 1.8 change in the height, that too on the outside, we were able to get slight improvement in the pressure drop. So some takeaways. So the data for the eccentricity equals to 0, they related very well with the open literature. And more importantly, that if my inner pipe is sitting at the bottom of the casing, we can have up to 75% decrease in the heat transfer and 25% improvement in the pumping power. And the last thing is we have also developed a new we have done some extra simulations with which we have concluded that we can generate swirls which can lead to supporting or lifting the central pipe up or make it centered automatically. This is part of a patent which is pending now at the European Patent Office, but there will be something that VITO will have in next year. Now, in terms of development, so as you can imagine, if you're going back to the same schematic what I showed before, we are basically modeling of this pipe, which can actually lead to this heat to conduct around the pipe and lead to, let's say, a more accurate simulation of these kind of pipes. So we are kind of now developing this within VITO so as to have a stream-wise periodicity also in the solid. And in future, it will be nice to simulate the fluid along with the ground in this case. And this is also important because these simulations now do not correlate 100% well with the system level simulation, which was performed by the other teams in the consortium. With that, thank you. If you want to know more of the project, you can go to hookloop.eu. Thank you.
Well done, Nitish. Very interesting. So we have 5 minutes, so at least a couple of 3 questions. Probably. You mentioned the problem with using a heat flux boundary condition, and I'm wondering whether convection boundary condition was not used then in the case, because that's, I think, the case for modeling for a convection boundary condition. So, like prescribing the temperature of an outside basin and then heat transfer coefficient through the material.
So, but what you're saying is right. This is what we also wanted. But with solid, we were not sure if stream-wise periodic solid would work or not, right? Because somehow you also need to be periodic in terms of solid. So does that assumption hold? And at that point, I was not sure that we just put periodicity and make sure that, just assume that it works. That was one of the, let's say, a bottleneck. So we are in the process of now verifying that from the ground up to see that it is actually valid and then run it for a heat exchanger case, maybe with solid and fluid optimization.
Another question? Albert?
Will we understand the marks on this ratio?
The outer shell.
On the outer shell. Yeah, on the outer shell.
What about roughness? Have you considered roughness in the pipes or?
That's also another thing. Yeah, but we didn't consider roughness. As well.
Make a difference, or it's just a matter of density?
It could be. It could make some difference, but yeah, cannot comment on it. I think right now. Yeah.
I can imagine it wouldn't be too difficult to build a relatively simple experimental setup to validate your simulations.
Yeah, sure, but
There's money in the project.
our work package is over, so I think we are done for now. But I'm sure there would be a follow-up projects, and there are also other teams who are interested in this kind of work, because I think it can be a big potential for these kind of closed loop systems for more shallow geothermal power plants. And we think that could be interesting, but this will be something in the follow-up project.
Power plants or heating plants?
Also, any kind of heat. I mean, let's say providing a hot water, then what you do with it, yeah, it's open for interpretation. So you can also put a heat pump and use it in the houses. Everything is possible after that.
Peter, what's the thickness of the insulation layer? Was that one already established to be like the optimum thickness? Because you can imagine the fact that you shrink it, there's less risk of hitting the outer wall, but before you have less insulation to the other cold wall.
Yeah, so that is optimized. There is certain minimum thickness in the insulation there that has to be maintained. It's actually vacuum in between the two pipes. There are a lot of optimization that has been done by other researchers. I'm just showcasing one case, but there has been multiple cases that has been studied. So there is one optima. I don't know if this is the one, but I think there's something else which is really optimum.
Good. Another question from you, Tom, and then I'll also have a question. Okay, make me a very simple first. So, what is like the thickness of this whole packet? Like, is it a given at the end?
I think there were numbers, no?
Okay, yeah, there were in the message, but I also didn't display. This idea, okay,
So 0.1 meter.
diameter. But then it's small. Yeah. And then maybe I miss why it is so difficult to maybe to put some support structure, like some.
So imagine you are 2 kilometers down, 2 kilometer horizontal, right? If you are able to put one pipe, that's amazing. If you have to put two and then make sure that one is centered to the other one, God bless. So, I mean, that's why it's difficult. I mean, that's why you cannot have any kind of, let's say, structures to support. It's very difficult to put something and then give it a 90-degree turn. And if you do not get that 90-degree turn, you do not get the benefits of this such kind of closed loop system.
Okay. Thank you, Donovan. That's my turn now. So now I was wondering, I was curious about this comparison between the results given by the correlation, so the VI correlations and the results of CF.
Mm-hmm.
So this is a case in which there is no streamwise pressure gradient, right? Because you're basically two concentric pipes, which results in a constant area channel in a streamwise direction.
Yeah.
What if instead I would induce a streamwise pressure gradient? I mean, a diffusing channel or an accelerating channel. What will be the accuracy of those correlations in that case? Do you have an idea?
So you cannot use streamwise periodicity then, huh?
No, apart from that.
Yeah, okay.
From that. It's an internal flow question.
I hope it will match. Also for some other pin fins, I think we have done some internal studies, and I think they correlate for most of the cases. And then if you have, like, say, multiple fins, for example, interacting, then you have a huge impact of turbulence, because it really kind of defines when does the flow the flow is becoming very turbulent, and then you have unsteadiness. If you are capturing everything, then only certain kind of turbulence can give you very exact match with the
But meaning that there are correlations can be, developed specifically for radial flows.
Yeah. So if you follow the work,
Because
if you
interesting.
but if you follow the work of Octavia, it's exactly this.
Thank you very much.
Thank you.
Thanks again for the very informative